336, palindrome pairs. Given a list of unique words, find all pairs of distinct indices, ij, in a given list, so that the concatenation of two words, word sub I plus word sub j, is a palindrome. Okay. So the thing that's a little... I mean, this is a potentially nasty one. I think the thing that I always complain about these older problems is that there's no n and there's no constraints, so that you kind of at least think about how much optimization you need to think about and do. Um, and also from this one, it seems that yeah, like for example, is it good enough to have an O of n square algorithm where n is the size of the input? Um, I don't know. And can we do better? Because there are a lot of optimizations that I'm thinking about now that I don't know if I'm willing to implement. Like for example, just like there are a lot of how to say this. And is it good enough to just try or n square, right? I don't know. And obviously, I would say if I was in an interview during this part, the questions that I'm kind of asking out loud now, I would actually ask the interviewer, like, okay, what are the constraints? Is n squared good enough? I mean, and usually they give you nudge you the right way. Well, maybe I won't ask that specifically, but I would say something like, okay, so first of all, the most naive algorithm is n squared because there's n squared pairings, and then but then you still have to do the matching to calculate the palindrome pair, and that'll take some O of 2 times t or something like that, where t is the length, the max length. So then it ends up being n squared times t, roughly, all of that. But it may be not fast enough, depending on the constraints of this problem. And there is some ambiguity, unfortunately, at least for me, in terms of right now, because this is not an interactive thing and no one's going to give me an answer about the constraints of the problem. But I will try to do the best I can. Um, let's see. I mean, because the thing is that the thing that makes it a bit tricky is that like, okay, yeah, ABCD and DCBA, they concatenate to to make a palindrome, but you can also imagine like AAAA. Oh, sorry. Let's see, like BAAA plus B, and that makes a palindrome, obviously, because that's just BAAB. But then, how do you how do you figure out how do you figure out in an efficient way that given this string, you need to look for B, right? Uh, and let's see. And then you have to do some math, or you have to do some pre-processing on each string, perhaps, to kind of calculate the things that you're looking for. Maybe that's okay. Because so what I'm thinking is, and maybe this is where you end up using the miniature algorithm, which is an algorithm that I still haven't mastered, to be frank, because it's such a like a niche algorithm. But for example, one thing that I might think about in my pre-processing is something like, okay, A, B, C, D. What makes this and what would I need to look for to make this a palindrome? Well, obvious case is CCBA, but then also another case would be just CBA, and then that's it, right? Because you do some, you know, there's just no more degree of symmetry or whatever you call it. Um, and then, but for BAAA, well, one solution may be AAAB, AAAB, AAB, and oops, AB and then B, right? And then it gets even more complicated, right? Because if you have something like, I don't know, banana, well, what strings would you look for? Well, I'm just trying to figure out this. The way basic is banana backwards, banana, and then minus the A, uh, and then actually maybe I'm wrong. Maybe this is actually. I thought there'll be one where maybe you skip the gap a little bit. Oh wait, no, this is wrong. No, that's right because this is not a. This is a wrong one, right? Because this doesn't. This is not an anagram. Oh, sorry, a palindrome. Uh, right. So actually, but is this one? This may be one. Yeah. Um, so so in this case, you can see that that's good, and B is good, right? So it doesn't even have to be, so there could be gaps. It doesn't have to be, you have to check something more naively. And from that, let's say you can construct this, um, but it's still, I don't know. I'm also thinking about stuff like suffix trees, but even then, I don't. I mean, suffix tree will help with the lookup, but and again, a lot of this what I talk about now depends a lot on the constraints, because there's a lot of stuff that you can constrain. Like, well, suffix tree is still going to be very expensive, so you want to do suffix array. Maybe that's more space efficient way of doing it. But those are kind of how we think about it. And then we have to pre-process each one. Uh, what is the best way to pre-process each one, right? Uh, like not even pre-process each one, just like during the search, like because there are two steps to this, right? One is knowing that I need to search for this, and then the second step is searching for it, right? Um, and the first step, I'm just trying to think about a little bit as well. Um, like what would make it, um, what would allow me to, what would allow me to figure out in a efficient way that I need to search for these strings for banana, right? I mean, the first one is obvious, just the reverse of the string, but after that, uh, right? Hmm. And I mean, the hard part again is knowing. So all the approaches that I kind of talk about and touch upon, they all have different trade-offs, and the question is whether or how do these trade-offs, um, well, these trade-offs, if you do it one way, you have trade-offs another way, and so forth. And at the end of the day, some of the trade-offs is complexity with respect to coding, coding difficulty, say, right? So that's something that if I had the constraints, this would make it easier to analyze which way the trade-offs that we should aim to optimize for. But as it goes, it's a little bit tricky as well. At least this is the way we would have to do if we want to figure out a way not to do n squared times L, for L is equal to the length of the max string. Because this will allow us to, in theory, do things in O of L squared, n times L squared, maybe O of L. because each one of the n words could have L different strings, and it takes L times. So it really depends on what the n and the l's are, right? Like to choose between n squared times L algorithm and a n times L squared algorithm, there are two different ways. Um, and that makes this problem a little bit tricky for me without kind of knowing what the constraints are. And yeah, and certainly, you could do tries and stuff like this, but again, it really depends on what they're looking for. And there is some, as a result, a little bit of mind reading on this problem, which it's hard to uh, mind read a problem when you don't know you know, like what I don't want to do, I suppose, is that I implement something for like half an hour and then be like, oh, no, you should have gone optimized the other way because they don't tell you what it is. Um, would like to think things have gotten better, but this is an older problem. So, hmm. Let me think a little bit about pre-processing. Oh, oops. Uh, Let me think a little bit about pre-processing. Pre-processing this. So the first step we have to do is that given like a random string, calculate what we have to look up. Um, and that reminds me a little bit of a little bit of one of those KPMP, but I guess that's what the manager algorithm is. But I refuse to kind of refuse to use it because it's an algorithm that really should not be a thing. I mean, it's helpful, but like why? Okay, so I think I'm just going to do something naive to begin with, and then we'll see what the performance profile of that is, and then kind of guess how we could optimize. So we'll do this in an iterative way. That's how I think I'm going to get started on this one. It is obviously not an easy problem, but yeah, but I'm going to pre-process the words and then kind of see. Okay, for word and words. Let's just have a lookup table. Uh, yeah, okay. Enumerate for each words. So we have index words. Lookup of word is equal to index, and then also pre-process. No, and then that's fine. And then for word, no, for index word and enumerate words. Let's just look at all possible. Oh, and I guess technically this can have multiple or distinct. Oh, they're unique words, so that should be okay. I was gonna have to do some math otherwise. Um, I'm gonna try to implement this naively just to kind of see what kind of performance we need to get to. And in this case, uh, yeah, let's just do it for L in length of in range of length of word. Is that good? Well, I guess we start with 1. Do we need the length of the word? I guess. Yeah. Okay. So now let's just say if is palindrome word plus word sub what's it called? Yeah, I guess we should. Let's just write suffix is equal to word the last L letters backwards. I hope that's right. Okay, let's just print it out real quick. for testing. DCD. Let's forget how these work. Let's do that then. I forget the interaction of having them together. That's a let's see what's not right. So we want this to be. Oh, I guess now we do it backwards. Then we could just do this. Okay, so that's good. Yeah, and then now we check if this palindrome of word plus suffix. Then we've just put it into the answer. Return answer. Answer that append index, and we want a list of this index and lookup of suffix, and of course we have to check that suffix is in lookup. Oh yeah, of course. Forgot to write the critical part. And then we'll check if a word is palindrome, and then we just do for L in range of might need to +1 that if word sub L is not equal to word sub I guess my negative L. Return false, return true. Okay, well, it should not match with itself, ideally. Yeah, okay. And look up. Okay, that's unfortunate. Maybe I have an off by 1 on my that, which happens. Yeah, this is, well, it would be nice if one of these returns true. I guess this one. And that's not even right. Oh, it's -0, so this should be negative. +1. Now it should be -1. Okay. Okay. It's a better start, at least. Okay. Now 3, 2. What is 3 and 2? 2, 2, and 2. So SLLS. Oh, that's interesting. We don't check for the other way. Okay, that's fine though. Because then we just have to check, well, we call it suffix, but we just check the same thing. Then if else, oh, oops, it's not else, we have to just check both. Don't know what I have to do for this one actually. It's possible that we might have to. Well, I guess clearly we have to. But it still doesn't. doesn't take my thing. Oh, because I guess in this case we want the prefix. Yeah, okay, fine. So then now we have to look it up. Oh, so that's wrong. What we actually want is first L characters, L plus 1 characters. Yeah, maybe. Right, even writing the brute force one is a little bit long. Okay. Mr. LLS. That is actually also wrong. What are we doing? So LLS, it still takes the we still do that. Because we want SLLS. Did I write the first time? Then why did it not work? Let's take a look. If this is true, that's fine. Oh, I see. This is actually maybe -1 or +1. Yeah, +1. Okay, so at least this got that good. And then now we just have to maybe do some deduping because of the way we check. But doesn't seem like it'll be fast enough though. But even this took 36 milliseconds. But yeah, it's a start. I just set this to set. Oh, right. I mean, these really should be tuples, but yeah, I'm going to change the tuples. There's just a lot of overhead. And now it give me the wrong answer, but let's see if it gives me the right-ish answer. And while that's running, I'm going to run the add more test case. Probably the server's having issues, right? Because even if it times out, it should time out faster. Alrighty. Well, I'm gonna try to refresh real quick because, you know. Okay, so that was much faster. I don't know, someone just timed out. Okay. Now let's try the other one. So yeah, so this works, but there's probably gonna be timing things. Let's submit it to see to get a big case that we time out on, and then see. Oh, I didn't know there was empty string. That's kind of. Is it really a unique word with this empty string? That is actually just a silly case. That's like one of those cases where you read and you're like, well, gotcha, and you're like, well, I learned nothing from this other than that the interviewer slash problem writer is kind of enjoying this a little bit too much. But how do we handle this? Eh, that is silly. Now I have to handle it manually, maybe. What a silly result. Okay, fine. Yeah, okay, fine. Um, It is 0, 0 divided by 2 plus 1, so it goes to 0. Negative 1 is outbound. Okay, fine. I hate everything about you. Yeah, okay. Now give me a timeout case. Ah, well. Okay. Yeah, this is a kind of a weird problem in that regards. Because to be frank, I just don't know what they're looking for. Because of the constraints, you can really go a lot of ways with the constraints of the ands and ls, and you could even say that like I just use a hash table, but you can say, you maybe could force a way to use a try or something like that, but it really depends on the constraints which are not given, and instead the kind of the trick case is the case where you have an empty string, which you could maybe even hardly say is a unique word per se, but maybe if there's constraints where they tell you that the length of each string could be 0, then you look out for it, because in common reading it's a little bit hard to disambiguate which one they mean. But yeah, overall, I mean, I think there's some merit in kind of the problem per se. I don't like the in terms of like if you're asking it or getting it on an interview. There are a lot of questions that you've kind of saw me ask in the beginning, and also while coding it, a lot of it complaining about constraints and stuff like this because again, there are a lot of different implementation detail types, and for each of those implementation, there are trade-offs either in implementation speed or space or time, and it depends on whether each some characteristic of the problem that you're given, which is like, well, if there are a lot of words, but each one of them are short, then you do this thing. And if there are a lot of, or there are very few words, but the words are long, then maybe you do this other thing, right? And these are trade-offs that I would talk about in an interview, just to kind of get a sense of which one to go. So I kind of guessed at one of the answers, and thankfully it went fast enough. It was 550 milliseconds, which is a little bit on the slow side, but it depends on, again, what the inputs are. But it still beats half the volume, so I don't know how I feel about that one. But yeah, overall, I think by itself this could be an interesting problem, but it really depends on, like a lot of interactiveness that this particular, like for programming contests, this had a lot of ambiguity that I would love to ask someone about, but you're not going to get it on the contest. So yeah, so that's all I have for this problem. Thank you.